So at this point, we've talked quite a bit about sort of the conceptual idea of acid and base strength, and also the relationship to equilibrium and equilibrium calculation. So how do you actually use K to determine the strength of an acid or how much of it dissociates? We're going to migrate into thinking about what happens when acids and bases actually react with each other. And the sort of big question is, well, what do you get? And the answer to that, well, it depends, and it really depends on the strengths, the relative strengths of both the acid and the base, what you get in the end. And this conversation is really going to lead us into two major topics to round out acid-base chemistry. One is buffers, which is what happens when you have both the acid and its conjugate base present in a system. Turns out that's tremendously important, especially in biology and biochemistry. But also this idea of titration. So how do we stoichiometrically add a known amount of acid or base to figure out how much of the other is there? And so that's more of a measurement technique. So we need to understand the chemistry of what happens when these two things react with each other. So to do that, we're going to walk through a few different sort of cases. And the first case is probably the simplest, and that's the case when you have a strong acid and a strong base reacting with each other in water. And so the example of that is HCl, which we know to be a strong mineral acid, sodium hydroxide, a strong base. And when those react together, this is all balanced already, we get water. That comes from the proton reacting with the OH group. And then we get the leftover salt, which is NaCl, aqueous. And this is sort of the overall reaction here. But we know from Chem 107 that we could write this out in an ionic form and write the net ionic equation, which would look something like this. And so remember, your net ionic equation, this is not the net, this is just the ionic equation before we've canceled like terms. We're just breaking each of these compounds into its ionic constituents to see what is actually reacting and what we call the spectator ion, something that's present on both sides. And so the net ionic we can go through and cancel like terms. So what we see is we have chloride and sodium on both sides of the reaction, so the actual net ionic equation is something we're really familiar with. That's just protons and hydroxide make water. So this is actually the inverse or the reverse reaction of water dissociation, right? Because water on the right side here dissociating into protons and hydroxide, in this case, are reactants. But it's an equation that we're very familiar with. But the key outcome here is that if we were to mix equimolar amounts, or the same amount of the strong acid HCl and strong base here, what we really produce is a solution of pure water. That's what the net ionic equation is telling us, because we have chloride and sodium on both sides. They're spectator ions. They're not actually doing anything in this reaction. So if we were to be asked, what do we produce when we add a strong acid and a strong base? Well, the answer is water. And if the question is, well, then what is the pH of that system? We should know that if this is what is produced, pure water, what is the pH of pure water? Well, we can think about it in terms of the autodissociation of water. We know that water itself, once it's produced, once you make pure water after this initial reaction of strong acid, strong base, it's going to auto-dissociate as we expect it to, and it's going to abide by the equilibrium, Kw, such that the proton concentration and the hydroxide concentration are both equal to 10 to the minus 7 molar, which we know, if we take the negative log of that, is a pH 7. And so what we know the outcome to be for strong acid plus strong base, as long as we're adding the same amounts, is that we get a neutral solution. And the reason for that, the major outcome, the important connection here, the reason why that's neutral is because what you've created is pure water in the system. That's all that's left over is pure water, and water dissociating by itself ends up having a pH of 7. So let's look at a second case now, getting a little bit more complicated, where we have a weak acid and a strong base. And so we know that the generic form for a weak acid is just HA, but what we know weak means here is that this will not fully dissociate, right? This will not break into its constituent ions completely, which is not the case for strong acids and strong bases. We can assume that sodium hydroxide, because it's strong, will break up completely into sodium ions and hydroxide. So the result is we're going to have some Na left over and H2O, and this would be our full reaction, but let's write out the net ionic. And that should look something like this. So we know HA in the full ionic equation, it doesn't break up completely. And so we leave it combined here. But we do know sodium hydroxide fully dissociates, so we can break that into its constituent ions. Sodium is on this other side, so that becomes a spectator ion. And we have some amount of A- that gets produced, but not 100% of it. And then we have water, which is just that little bit of proton that gets pulled off of here with OH. In the end, the overall net ionic equation for a weak acid and a strong base then is the weak acid plus the strong base makes some amount of the conjugate base here, the A-, and water. So let's look at a specific example of a weak acid or a strong base, and we'll use acetic acid, which is what vinegar is, and this is the molecular formula for acetic acid. So the net ionic equation then for acetic acid plus some strong base, we'll just write OH here, is going to be the conjugate base, which is the acetate ion in pure water. How could we figure out what the equilibrium constant is for this particular reaction? What is K? Would we expect this to be very product favored or very reactant favored? It's slightly different than what we'd done before with a weak acid, which was simply reacting with water, which was a weak base. So that would have been a weak acid and a weak base. Here we have a weak acid and a strong base. How do we figure out what K is from things that we already know? So we can start with the sort of simplest version of this, which we've talked about quite a bit so far, which is just a weak acid plus water. So this is just the dissociation reaction of acetic acid in water, and it makes its conjugate base and hydronium ion, and we can look these values up in tables or we can Google them, and so they're abundantly available. But remember, we're trying to get K for this other reaction, which is the weak acid plus this strong base, and we're going to call this Kn for the neutralization, because we're essentially neutralizing that acid by adding some amount of strong base. So how do we figure that out? Well, we have this reaction, and remember that we can add reactions together to produce something that we want, and if we know the K's for those, then we just multiply those together. So that's the tactic here, is what could we add to this reaction, the second one, that would produce this first one. So see if you can pause and think about that, knowing what we know, specifically think about water. So we know the dissociation of water. We know this to be true. We know Kw. So if we were to look at this and add it up, we would get the reaction that's the neutralization reaction. But notice that I wrote this dissociation of water reaction in reverse, and also note that I wrote it explicitly with water. So I could have written this out as just H2O makes H plus and OH minus, but in that case I would have had to write this first reaction without the water explicitly there, and this would work out the same way. And so in this case, if I look at this, what's going to happen is this H3O goes away, and then one of these waters goes away, and this produces the reaction of just pure acetic acid plus strong base reacts to make the acetate ion and water, which is exactly what we started with. So remember, when we add reactions together, we need to multiply their equilibrium constants to get the new equilibrium constant. Also notice that this I wrote as 1 over Kw, and that's because we know the dissociation of water, which is written in the reverse of this, water breaking apart into its ions, that has an equilibrium of Kw. But now I've reversed the reaction. Anytime you reverse the order of a reaction, you are taking the reciprocal of K. And so now 1 over Kw is equal to 10 to the 14. So in this case, Kn is going to be equal to Ka times 1 over Kw. So that gives me this really big number for Kn, 1.8 times 10 to the 9. And so what we've figured out here is for the neutralization of a weak acid and a strong base, the equilibrium constant is huge, which means that these reactions proceed to completion By proceed to completion, I mean they're heavily product favored. That this is 10 to the 9, that's a billion. So that means that there's about a billion times more product than there is reactant at equilibrium, which is very different than when we have a weak acid reacting with a weak base like water, which has a very reactant favored K equilibrium, where it's 10 to the minus 5. And so that's a major outcome here. So that means if you have a weak acid and you add a strong base, you can assume that they will react stoichiometrically with each other. It means every bit of the OH is going to consume the exact 1-to-1 amount of that weak acid, which it cannot be said when you have a weak acid and a weak base reacting together. So that's the important takeaway. So let's look at another example here, and let's take this one step further. Not just think about where the extent of this neutralization reaction is in terms of equilibrium, but also then what would we expect the pH of this solution to be at the end of that reaction. And so we're starting with a weak acid, which is HNO2, not HNO3, so this is nitrous acid, plus strong base KOH, produces this KNO2 and H2O. So this is the full overall reaction, but we could write this out as the net ionic. So 2 steps here. So I just wrote out, we know that HNO2 doesn't dissociate very much, so we keep that in the overall ionic equation. Strong base does, so we end up with spectator ions of potassium on both sides. So the net ionic is exactly the same form as we had before, weak acid plus OH minus the strong base, makes a little bit of the conjugate plus pure water. So let's figure out Kn for this. See if you can pause the video and figure out what is the neutralization equilibrium constant for this reaction. And let me give you really quickly what Ka is. Ka we can just look up online or in the back of the book for HNO2, and that's 4.5 times 10 to the minus 4. So pause it, see if you can get a net equation that looks like this one here, the green one, and a corresponding K form. Okay, so same exact sequence as we did in the previous example here. So I write out just the dissociation of HNO2. Notice that this time I'm giving you a slightly different representation just so you see it both ways. So before I wrote out the reaction of the weak acid in water. This time I'm not adding water here. Remember, those are 2 different ways to write acid-base reactions. They're identical. That allows me to write the dissociation of water in this form instead of the previous form. Same exact process here, get rid of the like terms on both sides, and we end up with the overall reaction, which is the same as the net that we were targeting. Now Kn is Ka over Kw, which turns out to be this huge number, just like we had before. So the equilibrium lies far to the right. So what do we have in this system then, if we assume we're adding sort of equal parts HNO2 and OH, because we know they're 1-to-1. What we have in the system at the end is NO2 minus, which in this case is a conjugate base, and water. And so this is distinctly different than what we had at the beginning of this video, which was strong acid plus strong base produced just pure water. And we said, well, if it's just pure water, then the pH of the system is 7 because of the auto-dissociation of water. But now we don't have just pure water when these two things react completely. We have water plus a base. It's a weak base, but now we can assume that the pH is going to be greater than 7. It's going to be basic. But how basic? Well, we'll cover that in this series of videos going forward, but we can assume then that this base is going to react with water to make a little bit more of this, and we're going to end up with a slightly basic system.